In this problem, we're trying to determine what force is necessary, Fa, applied at the top left corner of this box in order to tip the box over. In cases like this, where objects are tipping over, we can make a couple of assumptions. The first assumption we can make is that this object is going to tip at the lower right corner because our force is applied to the left side of the object. The second assumption we can make is that generally when a box is just sitting on the ground, there's a normal force along the entire surface of the box. But in this case, we can assume that the normal force and the friction force are localized to the bottom corner of the box, because at the instant this thing tips, we can assume that the only point that's still in contact is the bottom right corner of the box. So let's start by drawing a free body diagram, or adding some more forces to our object. We have a gravitational force acting through the center of mass. We have a normal force and a friction force acting at the bottom right corner, and we have our applied force acting at the top left corner. Now, when we're dealing with two-dimensional objects where you know the dimensions of the object, like we do in this case, it's often easier to use a lever arm technique of finding torques. So let's take a look at each force. If we were clever and we use the bottom right corner as our pivot point to sum torques around, the normal force and the frictional force aren't applying any torque. Their lever arms are zero as they go directly through the pivot point. The applied force and the gravitational force are applying torques. If we use a lever arm, which is really a perpendicular displacement between your force and your pivot point, the applied force has a lever arm of the height of the box, or 3 meters. The gravitational force has a lever arm of half of the width of the box, or 1 meter. So we can say that lever arm for the gravitational force equals 1 meter, and the lever arm for our applied force equals 3 meters. Now we're ready to do a Newton's second law equation for torques, which says the sum of the torques around our pivot point. It's going to be our applied force is going to rotate this object clockwise, so that'll count as a negative torque. Our gravitational force will rotate our object counterclockwise, so that'll count as a positive torque. And each torque can be found by taking the force multiplied by the lever arm, which we've already found. So we can say that the sum of our torques equals gravitational force times its lever arm minus the applied force times its lever arm. Again, we're looking for what applied force is needed to just get this thing to tip. So the limiting case is this is going to be at the borderline of being in equilibrium. And if we solve this for the applied force, get the applied force needed is going to be the gravitational force multiplied by the ratio of the gravitational lever arm to the applied lever arm. Putting in some of our numbers, this is a 100 kilogram object, so if we're using 10 newtons per kilogram for G, it'll have a weight of 1,000 newtons. 1,000 newtons times 1 meter over 3 meters, which will give us a, I'm going to call this out, a force to tip of 333 newtons. So this is a force that will put this object just on the verge of tipping. 301 more newton will make this thing tip over to the right. 1 less newton will not allow it to tip over at all. So there's our tipping force. Now, part B of this question asks us about whether this object is going to slide or it's going to tip. Now, to figure this out, we have to determine the maximum value of static friction between the object and the surface and see if the friction is going to max out before we ever get to our tipping force. So we can find the maximum value of static friction. In this case, if it's greater than our tipping force, the object tips. If it's less than our tipping force, the object is going to slide first. So let's get rid of some of this. To find the frictional force, we can use our normal Newton's laws equations. We can do a sum of the forces in the x direction, which is going to be our applied force minus our friction force. And this is just on the verge of slipping, so we're going to set those equal to 0, which just tells us that the applied force needed to make this thing slip is equal to the maximum value of static friction. We also have a sum of the forces in the y direction equation, which is going to be our normal force minus our gravitational force. And again, no acceleration up or down, so they're going to equal 0. this tells us that our normal force is equal to our gravitational force, which already happens to be 1,000 newtons. And our last step is going to use the definition of friction that says the frictional force on an object is equal to the coefficient of friction times the normal force. Coefficient of friction is 1/2. Normal force was 1,000 newtons. So our frictional force is equal to 500 newtons, which means the force needed to slide this object is also equal to 500 newtons. Now to see whether this object slides or tips, we just compare that sliding force to our tipping force. Whichever one is lower would happen first in this case, and the tipping force is 333 newtons, which is less than 500 newtons, so this object in this situation would tip over before it would slide.